So my name is Mike Malone, and I'm here to talk about storing multi-dimensional data sets that are extremely large, and our particular solution uses a non-relational database, and I'm sure you guys are super excited to hear more about this. So getting started. In the spirit of the event, which is, I suppose, to recount real-world war stories and mistakes and trials and tribulations, I've organized my presentation as a sort of narrative with an exposition explaining the context of what the problem we had was and the conflict and yada, yada, yada. So yeah, that's the tell you what I'm going to tell you part. My name is Mike Malone. I'm an infrastructure engineer at a company called SimpleGeo out in San Francisco. And for about the last 10 months, I've been working on a web-scale spatial database that sort of lives at the core of the products and services that SimpleGeo offers. It's our kind of core piece of infrastructure. And SimpleGeo is we're in the business of providing location-based services. So the company started out as a mobile gaming company, and Joe Stomp, who was the head engineer at Dig, and Matt Galligan, who was one of the co-founders of Social Thing, which sold to AOL, have sort of a lot of background in consumer-based web apps, and which produce a lot of data and are visible and require high availability and have a lot of the requirements that we've been talking about today. And they sort of got together and they had this idea for mobile gaming that used real-world location as sort of context. One of the ideas that Joe started building and had told me about was this idea for a location-based game where you could buy and sell weapons, and weapons would have ranges, and you could have these epic battles with your friends, but you'd have to upgrade your weapons, and you could only shoot them if you were within range. And that required location infrastructure. You needed to know where people were. And as they started building out these games, they realized that building out the location infrastructure was actually pretty challenging. They saw the gaming industry becoming pretty competitive, and the location industry, that ecosystem, becoming competitive, and decided to kind of change gears and, rather than entering that competitive environment, sell shovels during the gold rush instead. So that's sort of the backstory and just a little bit of context about what we're doing. And I guess as protagonist or narrator of this story, my goal is to sort of summarize the last 10 months of R&D work at SimpleGeo in like 45 minutes, which probably isn't going to really happen. So I'm leaving out a lot of details. Some of them are interesting, and that's sad. But I'm going to try to leave room for questions at the end. So if there's anything in particular that you're interested in, make sure you keep note of it. And when we get to the end, either ask me or come up afterwards, and I'll stick around for a little while. So most of the people at SimpleGeo have sort of built web apps before and built large-scale applications before. And we started with a couple of requirements for what we wanted to do in the spirit of not repeating past mistakes. So we wanted to build a system that from the get-go was highly available, fault-tolerant, decentralized, horizontally scalable, and one of the more important and I think often overlooked aspects is operationally simple, in the sense that it's easy to sort of reason about. When it fails soft. It doesn't fail hard, so there's no critical alerts that wake you up in the middle of the night and you're not putting out fires. Stuff like that, and it's easy to spin up new infrastructure and all of those characteristics that just make a piece of software sort of low maintenance. So we sort of did, because we're, the core is storing the data and really information retrieval, we did a survey of what database technologies were out there. And the two really broad sweeping categories are relational databases and the other databases, which I've called other structured storage options because the terms NoSQL and non-relational are both kind of wrong. So the relational databases, everybody knows them. Some people love them, some people don't. They're theoretically pure. They've been around for 50 years now. They're mostly standardized, pretty clean abstractions, robust contracts that, again, are easy to reason about and let you kind of know, what your data is going to look like. And they're battle tested. People run them at massive scale and with great success. And then there's the other stuff. Some of it is better than, some of them are better than others, and they have different characteristics that they emphasize. So we actually went with the other structured storage option. And the reasons are, ultimately the reason is because the relational transactional databases that existed simply didn't meet our requirements. So relational databases, and actually this should probably not say relational, it should say traditional or transactional or ACID compliant databases, are not highly available or fault tolerant without external management. They are centralized without external management. They can't scale horizontally without external management, and external management of these data stores is difficult to build. It's typically domain specific, which means you have to rebuild it every time you build a new application or want to add a new feature, and it's operationally complex. And not only are they not suitable, but given the contracts and constraints that the contracts they expose and the constraints that they adhere to, they can't do what we wanted them to do. If somebody claims to have written a high availability, horizontally, linearly scalable application on one of these traditional transactional relational database management systems, it's because they wrote their own database management system on top of it. That comes off as sounding a little bit like maybe condescending or like it's a bad thing, but I don't intend it to be. That's a perfectly viable option. It's just not something that we wanted to do again if we could avoid it. And just to put a little bit more weight behind what is here, just kind of 3 words, I'm going to do what I think every presenter has done today and explain what the CAP theorem is one more time. So at Principles of Distributed Computing in 2000, and just, I considered taking this out, by the way, but the terms are amorphous and vague enough that I just wanted to make sure everyone was on the same page with my particular interpretation. So at PODC 10 years ago, Eric Brewer said, yeah, there are these 3 desirable characteristics of databases, and you can only have 2 of them. And those 3 desirable characteristics were consistency, meaning that every node in a distributed or every node in a database system contains the same data. That is, replicas are in sync and never out of date. Availability, which means that every request to a non-failing node in the system returns some response. Whether it's a consistent response or inconsistent response. Availability simply means that a non-failing node returns a response. And partition tolerance, which says that the system properties, that is, or those are consistency and or availability, hold even when the system is partitioned and a node is down or the network breaks or one of those things that eventually happens in all large systems, and data is lost. And sort of a visual learner, the CAP theorem is kind of hard to prove on paper, but if you just sort of walk through the contract that relational databases expose, it's kind of an inevitability. So in 30 seconds, this is a typical scenario. You have a client, you have a primary database server, and a replica, and usually, suppose this server and replica, they're doing master-master replication. So the client writes to the server. The server immediately replicates that write to the replica and waits for the replica to acknowledge the write, and only after receiving the acknowledgement returns to the client and says that the write was acceptable. So this is a typical two-phase commit scenario. And that's the pattern with the transactional system. And actually, on the happy path, that's the typical pattern with a more eventually consistent non-relational database, too. It's really the failure case that differs. So in the case of a failure where, say, the server can't communicate with the replica, you have two options. Either the server returns, oh, hey, I'm unavailable, you can't write that right now, in which case the database system is unavailable. Or the server accepts the write anyways, in which case the replica is now inconsistent. The server and the replica have different data sets. And if for instance, that failure was a network partition, there might be other clients connecting directly to the replica reading that now stale data. And now ACID in 30 seconds. So again, these terms aren't formally defined. It's really a framework. They're not mathematical axioms. There's no real rigorous formalism to them. They've just been sort of written about over the last 40 or 50 years. But ACID stands for atomicity, which means either all of the actions are visible to another transaction or none are. So the transaction sort of happens at least logically all at once. Consistency, which says that application-specific constraints must be met for transaction to succeed, and in my mind actually is slightly different than what consistency means in the CAP sense, where consistency means that all nodes are in sync. Consistency in the ACID sense refers more specifically to the constraints that you place on your schema. So stuff like an integer column is actually an integer, and a string column is a string, and any range constraints. But that also includes stuff like foreign key constraints, so there's a little bit of an interplay and some overlap. But I don't actually read them as being exactly the same thing, which is a little bit confusing. I is isolation, which means that two concurrent kind of overlapping transactions will not see one another's transactions while in flight, that is, before they're committed. And finally, durability, which means that updates made to the database in a committed transaction will be visible to future transactions. So nothing will be lost or for that matter, even kind of partially invisible. So ACID is a nice little contract. It's a formalism that makes it really easy to reason about your data, and that's good. You're guaranteed to maintain a persistent global state as long as you define your constraints properly, and as long as your logical transactions result in, move you from one valid state to another valid state in your system. But ACID also hurts. Certain aspects of the sort of ACID paradigm encourage, and one might even say require, implementations to do bad things in the context of distributed computing. This is a quote, I'll just read it. It says, and I'm paraphrasing a little bit, but basically what it says is, unfortunately, ANSI SQL's definition of isolation relies in subtle ways on an assumption that a locking scheme is used for concurrency control, as opposed to an optimistic or multi-version concurrency scheme. This implies that the proposed semantics are ill-defined. And this isn't, these are the words, or rather, somebody who's not like a Web 2.0 hand-wavy engineer. This is Joseph Hellerstein and Michael Stonebreaker. Stonebreaker is a sort of infamous character in the world of databases. He founded Ingress, Illustra, Postgres, Vertica. His current toy is a database called VaultDB, and I think he's done some others in between there. And Hellerstein is a professor at UC Berkeley who was one of Stonebraker's students. Stonebraker was his doctoral advisor. So these are fairly respected people in the sort of transactional relational database community, saying that, hey, if you adhere strictly to these ACID constraints, you can't have real concurrency. You have to lock, and that's broken. And this is something that's actually been around since ACID was first proposed like 50 years ago, so it's not new. So in a nutshell, it's a question of values. For the sort of traditional databases, cap consistency is the holy grail. It's maximized at the expense of availability and partition tolerance. At scale, failures happen. I like to say, when you're doing something a million times a second, 1 in a million failure happens every second. So we're sort of witnessing the birth of a new religion when it comes to the philosophies that people sort of get behind when they're building these large-scale complex systems. And in that context, cap consistency it's a luxury. It's really nice to have, but at scale, if you want to make sure your system's always available, and failures are a reality of life, you can't have it. That said, religious wars are never a good thing, and there are contexts where one or the other is a better alternative, so horses for courses. And also, always say, keep in mind that in the happy state, when there aren't failures, the various databases tend to behave very similarly. It's really when a failure occurs that you have to make this trade-off. So that's really all I'm going to say about the whole why we went that route bit. And I think everyone's kind of heard that story. So forward. I kind of skipped the part where we did a survey of all of the various non-relational databases because there are a lot of them and it's a whole other talk, and really there's not one that's absolutely better for every use case than any other one. So just in the interest of time, we chose Apache Cassandra, and Cassandra is a distributed hash table. It's a key value store, and it's basically a big dictionary in the sky, and it's a really great distributed hash table. So some of the characteristics that we really like about it is it has this gossip protocol that provides a peer-to-peer network overlay sort of abstraction that does fault detection and is resilient to failure scenarios. And it's a completely distributed peer-to-peer network, which means there's very minimal operational overhead. You can just spin up a new node and say, hey, I want you to join this cluster, and it does. When a node goes down, you can just kind of ignore it, and the cluster will repair. So that's nice. It does, by default, out of the box, it does random hash-based partitioning, which gives you at least some measure of sort of auto-scaling and online rebalancing, where when you add a new node to the cluster, a section of the load is distributed to it. It has a pluggable replication strategy, which was important for us because we wanted to replicate to multiple data centers. We're running completely on EC2, and occasionally US East 1B will just disappear for a little while. So we wanted to make sure we had all of our data in multiple locations, and it's all multi-homed. Cassandra also allows for tunable consistency levels, and this is on a per request, per read, per write basis. You can say whether you want consistency level 1, which means one server written to, responded from before an acknowledgement. You can get a quorum, or you can say all replicas. So as a peer-to-peer, I think I said this already, as a peer-to-peer system, operations are decentralized, and it has good failure handling, and we like it. And like Theo said earlier in his talk, I also like software that has some academic rigor. And I don't like to write software or run software that I don't really understand and can't dig into. And Cassandra has both of those characteristics. It's based on Google's Bigtable, well, sort of a melding of Bigtable and Amazon's Dynamo. It was written originally by some engineers at Facebook, one of which came from Google, and one of them came from Amazon. And it's got a lot of sort of academic background that went into it and thought. And it's also, so one of the distinctions I like to make is MySQL's query processor alone is 100,000 lines of C. The entirety of Cassandra is about 30,000 lines of Java, which isn't that much better of a language, but it's a third of the size of the query parser in MySQL. So it's a lot easier to sort of wrap your head around. But there's a twist. Cassandra is not a spatial database. Distributed hash tables intentionally destroy all data locality, or at least as much as they can. They run keys through a random hashing algorithm. You know, it's a typical consistent hash scenario where your nodes have an identifier. That identifier is hashed and put onto a hash ring somewhere between, say, 0 and 2 to the 256 minus 1. And then the keys that are being stored are also hashed, put on that ring, and they actually get physically stored on the node that either precedes or follows it on the ring, depending on which direction you like best. And that gives you really good balance. When you add a node, it sort of picks up a section of the writes, and sort of at the limit, statistically, you get perfect balance, at least in theory. And it works really well, but what you end up with is if you have Bob, Sam, and Alice stored in the database, they don't get stored in any sort of real order. They just get, well, their locality is destroyed. Which means your list of supported queries looks something like this. You can do exact matches. You can't do range. You can't do proximity queries, and you can't do anything else that's not an exact match. So you can look up Alice if you know Alice's name. That's not much use if you want to, say, find the nearest Starbucks. So that was a big problem. And when we were sort of surveying the options, we came across this thing called the order-preserving partitioner. So like the replication strategy, Cassandra has a pluggable partitioning strategy. And the partitioning strategy is the bit of the system that is responsible for mapping a key to a node, and I guess I suppose also mapping the node to the ring. And the default option is a random partitioner, which, like I said, uses a consistent hashing strategy and gives you really good balance at the cost of destroying locality. The order-preserving partitioner is sort of the complete opposite end of the spectrum. It stores everything according to its natural ordering. You have to balance the cluster manually, so you give each node in the cluster a token, which is like, you know, its position on the ring, and data again goes to the node that lexicographically follows it, but rather than hashing the keys, it's just the natural key is used. And because the data is arranged according to its natural ordering, you can perform range queries on it on a single dimension. That is the key. So it gives you exact matches. You can do range queries on that dimension, and you can do proximity. You actually can do proximity queries as long as your sort of similarity, your metric for proximity is lexicographical ordering. So, yeah. So we had this mechanism that allowed us to do single-dimensional lookups, but spatial data is inherently multidimensional. Or is it? And actually it is, but we'll get to that. So typically when you think of a two-dimensional space, you lay it out in the way you learn in high school math or elementary school math or whatever, on a Cartesian plane with an x and a y axis, and a point has coordinates on both of those axes, and that's how you identify the point. But if you have a constrained space, there's another way. You can draw what's called a space-filling curve, which is just a line that touches every point in your space. And rather than using the multi-dimensional address, in this case two-dimensional address of a particular position, you simply measure the distance along your curve. And at the limit, space-filling curve will touch every point in your multi-dimensional space. So this is sort of the second iteration. You can see the small z's, and the small z's form a bigger z. This is called a z-curve, very imaginative. And then we discovered this thing called geohashing, and it's kind of neat. The sort of chain of logic here is that by interleaving the decimal bits of coordinates, latitude and longitude, you're left with the equivalent of doing a binary pre-order traversal of a tree, and like choosing 0 for left, 1 for right, and that is also the equivalent of a z-value or a z-address. So they're sort of isomorphic concepts, and then it's kind of neat. And then if you base 32 encode that binary representation, you have this convenient little identifier that's a single-dimensional, lexicographical, sortable identifier for a coordinate, and it's arbitrary precision. You can go as far as you want, and it's robust in the sense that it's reversible because you have full information. There's no information lost by just interleaving the bits, and that's pretty cool. And that allowed us to do stuff like multi-dimensional range queries. So if going back to just the first iteration of the z-curve, you have 1, 2, 3, 4 like this. And if I'm querying for everything in that gray area, I can just query for everything that's in 2 and everything that's in 4, and do a little bit of filtering. In Presto Changeo, I've eliminated the need to traverse half of my space. But there's a catch to that, too. The locality characteristics of z-curves, while good, are not great. So you can have 2 points that are close to each other in two-dimensional space, like these 2 points, the 2 x's sort of on the right, that are really far apart on the one-dimensional z-value sort of space. You can also have 2 points that are really far apart in your two-dimensional space that appear to be right next to each other in your one-dimensional space. And those problems, while annoying, they're more or less tractable and solvable on the client side for range queries. With a little bit of pre-processing to sort of compute multiple queries, like in the situation back here where I did one for 2 to 3 and one for 3 to 4, and then some post-processing to do a merger. It's not the best solution in the world, but it works, and we got all of the other nice things that Cassandra gave us. But it gets worse when you add additional dimensions, and it gets a lot worse in the degenerate case when you're trying to do a proximity query. So in the case of a proximity query where you just want to find the nearest neighbor to a point, I mean, this is also true of like similarity searches. You might have something like this where the sort of top x is what you're querying for, and the bottom one is the nearest neighbor, and in between those 2 points on the z-curve, you have a bunch of other data. And that other data is completely irrelevant, but you have to walk through all of it before you get to the nearest neighbor. And that's annoying. And again, in the degenerate case, it can be really quite catastrophic in terms of request latency. And even worse than that, at least as far as our initial requirements of sort of operational simplicity and good balance and decentralization and stuff, is it's on the opposite end of the spectrum in terms of locality. So the order preserving partitioner doesn't really help you at all with balancing. So if San Francisco is where the stat is and there's a whole bunch of activity going on in San Francisco, all of San Francisco and everything near San Francisco is going to be mapped to the same location on your ring of nodes, and that individual node that's handling all of San Francisco is going to quickly become overloaded, and the rest of your cluster is going to be sitting there bored, spinning its wheels, doing nothing. And that stinks. You then get into the scenario where you have to go in and you have to move tokens around and sort of jigger things, and there's not a whole lot of transparency into what data is where and you know where you should move them, and you start going down the road of like, oh, maybe I can write something that like crawls everything and like sees what data is in the system and then you know do something clever to figure out what the token should be, but that's kind of you know, treating the symptoms. So we were kind of frustrated and annoyed and having issues, and it was kind of a turning point where we realized we needed to kind of start over and rethink things. So after some Googling and some research, I discovered, Theo again was talking about sort of academia and looking to other areas of computing and I think other disciplines for solutions. I found actually a good amount of research on this topic in the context of peer-to-peer distributed systems like BitTorrent and Napster and stuff like that, and some more recent stuff. I also found a lot of interesting research in computer graphics because they have to solve a lot of the same problems with dimensional data, particularly with stuff like ray tracing, where you're shooting a beam of light through space and you want to see if there are any objects that it's going to intersect with and bounce off of. You're sort of stepping as you project that beam through space, and for every step you have to do a lookup of all of the objects that exist in your space and see if one of them intersects with this point. So there's a lot of overlap in that field too. But around this peer-to-peer indexing and stuff, found like two sort of really broad categories. There's an OVER-DHT, DHT being distributed hash table indexing paradigm, where people said, oh hey, we have this distributed hash table, maybe we can kind of put a more, overlay a more sophisticated data structure on top of it, much the way you would create a set out of a dictionary. And then there's this other paradigm of overlay dependent indexing, where you create a peer-to-peer network overlay that has sort of semantic knowledge of what your index looks like. And they both work, and it seems to me from the stuff I read, the concepts are fairly isomorphic, with mostly linear factors kind of differentiating one or the other, making one better in certain circumstances or worse. Like I said, it's sort of like building a set out of a dictionary. Actually, it's almost exactly like building an ordered set out of a dictionary, building an index out of a hash table or a distributed hash table. Unfortunately, what I didn't really find was any real agreement on a solution that was absolutely better, and really very little discussion of techniques that were sort of qualitatively good enough for practical use either. So we sort of tossed around a lot of ideas. One of the things we thought, we sort of reconsidered options that we had discounted before, and thought, what if we did sort of an overlay-dependent grid using a cluster of PostGIS servers, because PostGIS already does this spatial indexing stuff. And the conclusion we got to was, yeah, that might work, but the relational transaction management system, that little bit that implements the ACID contract, and the access methods, which are the fancy name for like B trees, KD trees, or the sort of data structures that the databases use to index the information that they're storing. They're tightly coupled to one another, and they're also tightly coupled to the concurrency systems within the transactional databases, and tightly coupled to the repair mechanisms like the write-ahead logging and undo logging and stuff that exists in those systems. So basically, it would be a massive rewrite. It would involve ripping out large portions of the code that are extremely complicated and have been around for 15 years or whatever. And this problem isn't really specific to PostGIS. It's kind of true of transactional databases, and I think databases in general, where the structure of the storage subsystem is very tightly coupled to the way information is retrieved and the way information is repaired, largely for efficiency. So the other option was to not couple so tightly with PostGIS and treat it as a black box and write an overlay on top of it. But again, we're back to implementing peer-to-peer network with failure recovery and detection and fault tolerance and resilience. And Cassandra already had all of that. And again, it's probably clear by now that I think that those problems are at least as difficult, if not more difficult, than actually storing structured data on disk. So because we had this distributed hash table, I dug more into the kind of prior art on the distributed hash table overlays. And like I said before, the academic world has kind of beat the crap out of this particular horse, and there's tons of papers on peer-to-peer indexing in distributed hash tables going back like 15 years. But this is true in general, and I think it's particularly true in this case, and in the case of databases. Academia is obsessed with like provably, deterministically, asymptotically optimal solutions. And in the case of a real-world system, you tend to have these like high-level business requirements, and you want something that's probably good enough to satisfy your high-level requirements most of the time, for some value of probably in most of the time. And if that probably good enough algorithm is, several orders of magnitude easier to implement, it might mean the difference between, a project that takes a month to implement and works, and a project that takes an entire company years to implement, or is just simply too complicated with the abstractions that currently exist. So you might even consider the simpler one, qualitatively better. So having dug through all of that, it was sort of this overwhelming, like, holy crap, there's so many different variables, there's so many options, what the hell should we do here? And I kind of stopped and put aside all the papers, having learned a lot from them, and just said, like, all right, let's like boil this problem down to its core. So we have Earth, and Earth isn't actually flat, but that's a whole other talk. The whole spherical geometry thing is another pain in the ass. So for now, the Earth is flat. And when somebody creates a new layer in our infrastructure, this is basically what they get. They get a blank slate. It's kind of an overlay of the planet, and there's nothing in it. It's kind of like a new table in a database. And they start adding records or spatial data to that bucket that represents the Earth. And as long as there's not too much data in that bucket, we don't care. when we get a query, we'll just pull it all back, and we'll interrogate each one of the records, and we'll filter out the stuff that's irrelevant and return the stuff that's relevant. And then at a certain point, they've added so much data that we don't want to have to do that every time we run a query. We want some sort of higher level semantic filtering mechanism. So what if we just split it in half and made 2 buckets? So that's tractable. That's something that we can reason about, and it's not a new idea. It's a tree. So what if we do that? So the mapping became something like this. We have this multidimensional space that can be split some number of times, because we'll then recurse. When one of those buckets gets too big, it will split again. And there's some identifier for each one of the sections, and that maps to a tree, and the tree has, that tree identifier maps to some part of the ring. And at this point, and so the data model looks something like, there are nodes in the tree, and each node has metadata about the state of the tree, saying that this node is split. It's an internal node, or it's a leaf node, and if it is split, it'll have, some sort of pointers to the keys of the children, and perhaps some additional statistical information about the data that's below it. And then nodes can also have data items that are being indexed, and those are just structured byte arrays that have attributes and identifiers that map to sort of a canonical object. And this is just a side note. To simplify sort of caching and traversal logic, we decided we'd keep data only in the leaf nodes of the tree. And when we started going down that path, we realized, hey, this is kind of like a concurrent tree that we see all the time in like Java and other languages, where you have multiple threads that want to kind of cooperatively work with the data structure, and they don't want to lock the whole data structure whenever they're adding something or reading or whatever. So they're optimistic, and they just kind of try to do stuff, and they're eventually consistent. When they traverse the tree, they're guaranteed to kind of get to the end, but if something gets added in the middle, they might miss it, and that's okay. So yeah, not really a new idea, but that was good. We had some prior art to look at. So in this system, the splits are optimistic, they're idempotent, and they're fail forward. So when a node gets too big, instead of locking the tree, the splitting node it registers that it's splitting, and it starts replicating any write that it receives. It writes it to its own sort of bucket, but it also sends it on to any relevant child or children buckets during the duration of the splitting operation. And once the split is completely done, which means that all of the data has been moved and all of the interested parties have been made aware that the split has occurred, at that point it's registered canonically that the split's done, and then we can clean up the data that used to be in this internal node, and we can remove it. And what we realized is once we did that, we had this sort of tunable knob that is the bucket size that allowed us to balance locality and distributedness. So any data that is in a single node of the tree is going to be stored physically on disk right next to each other. And data or sort of separate nodes in the tree, because they're keyed into this distributed hash table, are randomly distributed across the tree. So we have really good balance, and if San Francisco becomes a hotspot, then it'll split more deeply, and the subsections of San Francisco will be distributed around the tree. So almost immediately we realized that we have this issue of the root of the tree. It becomes a hotspot. Because for a tree to be useful, for you to use it in any real meaningful way, you have to traverse it. And typically in a tree traversal, you start at the root. And in our particular case, the only node in our tree that was really discoverable was the root, because we didn't know the state of any of the child nodes. We didn't know whether the root was split without asking the root if it was split. So it kind of limited our options. But yeah, traversing through the root meant reading the root, and reading the root for every traversal, which is a read or a write, was unacceptable. So again, went back to ACM and Google Scholar and saw if there's anything existing that addresses this. And there are sort of a lot of academic solutions. Again, the most promising was this concept of a skip graph, which is a generalization on a skip list and stores sort of multiple levels, a skip list being sort of a B tree index into a list, more or less. And so it's multiple levels of skip lists for each level of the tree. But the problem was it required O n log n data, because you needed log n data at each node in the tree, and there are n nodes, so you had n log n data, which was too much. So we kind of didn't want to go down that road. Another proposal that seemed sort of promising was defining a minimum tree depth. So instead of traversing through the root, you never stored anything at the root, and you had, instead of a tree, sort of a forest that started, say, 3 levels deep or something, and then you had a little bit of distributedness because you can traverse through the root of the sub forests or whatever, the sub trees. The problem is it's kind of a band-aid on a bullet wound, because you've just moved, instead of having one hotspot, now you have, say, 8. So if you had a degenerate condition where somebody was, say, storing all of their data in San Francisco and they have 1 billion records, there's likely only going to be one sort of route for the San Francisco area, so it didn't really help us. And this was really the hardest problem for us to get a handle on. And what we came up with was just something stupidly simple. And I like stupidly simple solutions, so that's okay with me. And the stupidly simple solution was to just keep an LRU cache on each physical node that's doing traversals of nodes that have been traversed previously. And instead of starting traversals at the root of the tree, start traversals at the most selective relevant node. So if you're doing nearest neighbor query for 0.27, then you would start at the smallest child node that you've seen before that contains the 0.27. And if that node doesn't satisfy you, instead of traversing down the tree, you traverse up the tree. And along with the result set, once you eventually return it, you return a list of nodes that were traversed, and that way the caller can add them to its cache. And we thought of other caching schemes too, but LRU was nice because no semantic knowledge really of the application aside from this thing was accessed at this time, which was nice and generic. And the performance characteristics are such that on the best case, in the happy path, everything's cached and there's 0 read overhead. And it's essentially as efficient as writing directly to Cassandra, which is very efficient. And in the worst case, when nothing's cached, you traverse through the root and you get O log n read overhead, which isn't horrible. It just means you have the potential for a hotspot if nothing is ever cached, which, like, once you've traversed once, you've at least cached the next level of the tree. So that doesn't happen. And rebalancing became almost unnecessary because in a typical tree scenario, if you end up with sort of very different depths on either side of the tree, in order to get good performance, you need to sort of rotate the tree and kind of even out the depths. But in this scenario, the caching sort of pulls the nodes that are further down back up to the top of the tree, and rebalancing becomes less of an issue. So we've been able to get away without doing that, which is nice, because for a concurrent tree, the only real way to rebalance is to rebuild the whole tree. That might be wrong, but I think that's true. But that means traversals have to go both ways, which makes them slightly more complicated. So they have to go up and potentially down the tree if they hit a split. So we pushed a little bit of logic, a little bit of complexity to the traversal. So I'm running out of time, so I'm going to quickly run through the rest of these slides. So this is sort of what a traversal looks like if a node this is a nearest neighbor query, and that's mapping the two-dimensional space to the tree. So the X is the point, the origin of the query, and we're looking for the O that is closest to it. So the node in the tree that contains it is that bottom sort of left, right, left node that is clearly identified. And so we start by querying that, and we find this O off to the left in that bottom left thing. And if we draw a circle around that, sort of centered at the origin of the query and just intersecting that O, we have a circle that overlaps other nodes that might potentially have a result that's closer than our O. So there are some of those, so we need to traverse up. So we kind of redirect the query to the parent, which redirects it to the right child, which returns that O in the right child, which does happen to be the nearest neighbor. And when we draw another circle intersecting that one, we now have a tighter radius because it's closer. We see that that circle doesn't intersect anything that we haven't already looked at, so we have the nearest neighbor. And we're done traversing, and we've only hit 2 nodes. And that's irrespective of the depth of the rest of the tree. That gave us exact match queries, range queries, proximity queries, and as far as I can tell, the strategy is generic enough that we could implement pretty much everything I've come across that exists in sort of the standard arsenal of indexing tools, and in multiple dimensions, and optimally. We have a KD tree implemented, which goes up to about 8 dimensions before starting to really degenerate to really poor performance. And we've also met all of our desirable characteristics because it's built on top of Cassandra, which met our characteristics, and we're resilient and fault tolerant and optimistic, and we're not locking anything. And that's pretty much my story. But we do have ideas for some future improvements. So I think a lot of these concepts will generalize to graph traversal instead of just tree traversal. I think we'll be able to do aggregations up the tree, bubbling information up to the top so that we can do sort of summary information. And I also have some sort of lessons learned, mostly about stuff that we've already heard today about how complex systems sometimes behave badly and scientific method, blah, blah, blah. Also, thread-based concurrency sucks. And then I think an important thing, like at least my approach to sort of building these big systems, is to learn from the real world. because the real world scales. And when you're stumped by a scaling problem in sort of the specific domain of a computer, think about how you'd solve it in the real world. Like governments and other larger organizations are decentralized and have asynchronous communications, and they tend to work. So think of the patterns that they use. Scale problems they exist and they're solved in the natural world. And just think to yourself. I do this all the time. If I'm looking for the nearest Starbucks, well, how would I do that myself if I'm sitting at my desk? But also be aware of sort of failures in the other domains too, political failures and stuff like that. Because again, very sort of similar communication patterns. And that's about it. And I have, I think, 5 minutes. So if anyone has any questions, I'm all ears. Nothing? Come on. So most of it's in process with Cassandra, so it's in Java, although I kind of wish I had looked at other options. It grows and shrinks depending on various factors, but I think right now we have in the index cluster like 15 nodes. So the question was whether it was being implemented in Cassandra as a pluggable application strategy. And I'm guessing the side question to that is something about whether it's going to be available to other people, or no, all right. So I won't answer the second question then. Not really. It's more generic than that. It's really just a distributed hash table overlay. It's sort of co-processing alongside Cassandra, really for efficiency, and because it needed to hook into a couple of sort of callbacks for like cache invalidation and stuff, specifically like after replication, caches needed to be invalidated, and the easiest way to do that was to kind of run it in the same memory space. What up, Cliff?
Yeah, so did you write all new, are you using all new write paths and all new read paths, or did you just modify them?
Question is if we have new read and write paths, or did we modify the ones that are in Cassandra? And the answer is we did neither of those. We just used the ones that are in Cassandra. So it's just using the random partitioner. If you're familiar with Cassandra, the nodes are rows or things identified by keys, and the actual indexed data are columns in the rows that have a name, and in our particular implementation, at least at this point, all have null values. And that the columns are actually sorted they're sorted by, again, a pluggable comparator. So you can get another dimension. You can sort of store things sorted already. So you can have your buckets sorted too, which you can get a little bit more efficient querying from that too. So the question is, when you put the data into the index, is it automatically generated for you? Is it something we built, or is it something in Cassandra? So Cassandra uses Thrift, which is like a RPC sort of abstraction layer, and like domain-specific language that you then generate code for different languages. And we added some Thrift interface, and then like a thin wrapper, and it builds the index in process, sort of on top of Cassandra. Yeah. So it's almost as if Cassandra was embedded within this system. I think we got to wrap things up because I'm on a NoSQL panel upstairs in 1 minute and 6 seconds. But I'll stick around after that if anyone has any more questions.